Okay, on this video we are going to continue with the applications of spring mass, but now I'm going to add a damping model, amortiguamiento in Spanish. Okay, now the concept of friction. Friction is a force that opposes to the movement and goes in opposition because it's supposed to be a friction. Now I'm going to do an experiment here. Now, according to Galilei and other scientifics, you cannot see here when it's going to hit the floor, but the concept here is, and you have to answer your question. This question is, which one is going to fall first, the sheet or the pencil? Okay, the answer is very straight. The one that falls first is the pencil. Okay, so Galileo was incorrect. He didn't know anything, or he was in a mistake. Well, the answer is the friction, because the sheet has a different property than this. Now, let me do the same test. This is the sheet. Now I'm going to do this. Okay. So which one is going to fall first? Okay. And actually, they fall at the same time. Okay. So I think. So what makes the difference here is this. So same sheet, but this one is made like a ball. Okay, now this is still the sheet. So what is the difference here? The difference is here. When it is going to fall, what is going to happen is that this ball has to cut through less air. So the air that is below is small, so it's going to fall and it's going to remove the air below the ball. But when this one is going to fall, here, take here how many air has to replace or to move away so that it's going to fall. So that is why it's very slow to fall. So what happens here is that the air is actually making the opposition of the movement. So when it's going to go down, then this air has to be displaced. So that is going to be opposite to the movement. On the contrary, here, the air that has to displace or remove on the pad is going to be less. Or the pencil, here, the amount of air, or even like this, is going to remove less air. Alright, so what happens here is the friction for the spring and mass models is the quantity of air that you have to remove in the movement, on your path of your movement. So let me write it. In this case, the friction is the quantity, the amount of air to be removed out of the path of movement. Okay, so we have here the ball is going to fall, and here we have a piece of sheet that is going to fall. So obviously here the quantity of air below is just like this, it's going to go like this. But this is the quantity of air is a lot more, so it has to do this. So that is why it falls slower. Alright? Okay, now that is the amount of air, but one concept here is that the faster the movement, the more air has to be removed. Therefore, more friction force Okay, now if this sheet is moving faster, so if this sheet is falling slow, then the air has to is removed is easier. But what if it's moving faster? If it is moving faster, then the air has to move out of the path quickly. So that means that it is going to have more friction force. Now, if you remember when you were kids and when you were in the car, and you take out your hand and you do this like this. So I remember I was playing like this and just feeling the air in my hand. All right. Now what happens there is that when the car was moving slow, I didn't feel anything. All right. But when the car was moving faster, I can feel more friction. So here what happens here is that the faster the movement is, the more friction you will have. So you will have to remove more air quickly, right? So that is the concept here. In this friction of the movement is that the friction force, I'm going to make this FF, friction force is proportional. I'm going to write beta, no, maybe not beta, but another number, mu, the speed times the speed. Right now, this proportionality means is different because it's not the same that if you fall with the air movement or if the ball it is actually falling inside water. All right, so it's different. It's the density, because if this is water, then it's going to fall slower, because you have, instead of removing air, what you have to remove is water. So that is more difficult. So that is why the friction force is proportional. This proportionality is the medium, is the environment conditions of what you have to remove in your path of your movement. All right, but in either way, that friction force is proportional to also the speed. So the faster, then you have to remove quicker the air or the water. Okay, now because the friction force is always in opposition, then it is going to be negative again. All right, so it's going to be minus mu, the speed. The speed is actually the derivative respect to the time, the first derivative. So here you have your friction force. Okay, so what happens to the model? So what happens to the model? You have your spring here, you have your mass, okay, your equilibrium point x equal to 0, and here what I'm going to add is a symbol for the damping force. This symbol is actually a motivator, a damping force. Okay, so here you have the K of the spring, and here you have your mu of the friction force. All right. Okay, so what happens here is that according to the second Newton's law is that the sum of all forces is equal to the mass times the acceleration, and the acceleration is the second derivative of x respect to the time squared. So that is going to be equal to, here is the minus kx from the Hooke's law, and we are going to add the friction force. In this case, this part, minus mu derivative of x respect to the time. So that means that the mass times the second derivative of x respect to the time squared plus this to the other side. Now this is negative because the friction is always in the position of the movement. Okay, so this to the other side is positive, mu derivative of x respect to the time, and this kx plus kx equals 0. And what you have there here is the formula that we are going to use to solve this kind of application. So you will have the mass is a constant. Here you will have the friction force, which is also constant. All right, I don't expect that the air is going to change to water in the movement. It is possible, but I don't think that is going to happen. All right, and here the Hooke's constant here. All right. Now it's a second order differential equation with constant coefficients. All right. Now remember that we will have three cases. Case number one, if you remember, real distinct roots or different roots. All right. So you will have, your solution is going to be something like this: C1 exponential of m1x plus C2 exponential of m2x. So what happens here is that this is going to be just an exponential negative. By the way, here the m's are going to be negative. Here of the characteristic equation. Why they have to be negative? Because exponential has to be negative, because the movement has to go through the equilibrium point with x equal to 0. So this is x and this is the time. Right? So it's going to be always to the, it's going to go always to the equilibrium position. All right. So that is the case number one, and this is in mechanical engineering. This is overdamped case. Overdamped case. Now in mathematics, it is real different roots, but in mechanical engineering is overdamping case. Sobreamortiguado in Spanish. All right. So what will happen here is that when you have this case, this means that your car is brand new. The amortiguators are brand new. So if this is your car, then what will happen is that if you go in your car and you cross with a rock, then it's going to move, but it's going to go very fast to 0. So you don't have problems there. Now remember that you will have, this is case number one, real and different roots, but you will have case 2, and that is real repeated roots, and your solution is going to be something like this: x homogeneous is going to be C1 exponential of x plus C2 x exponential of x. Okay, so what happens there is that this is something like this, and it's going to go to 0. So this is in mechanical engineering. This case is called critical damping. Critical damping. And what happens there is that if this is your car, if you cross a rock, you are going to jump, but it still goes to 0. All right, it still goes to 0. So that means that your amortiguators are being, they have some degradation, so they are not responding as quickly as this. All right. Now remember that we have case number 3. Case number 3. Imaginary roots. So what will happen here is that your homogeneous solution is going to be exponential of alpha x C1 cosine of beta x plus C2 sine of beta x. Alright? In the plot, what will happen here is that you will have a combination of something that have some oscillation, is moving, jump up and down, but then you have an exponential, and the exponential happens to be, all of them has to be negative, engineers. All right. Sorry, this is m1 and m1 because it is repeated. Okay. Now the exponential is negative, so it's still going down to 0. But here the behavior is different, because the behavior is going to be something like this. It's going to be something like this. So what will happen if this is your car and you pass through a rock in the movement, so what will happen is that this is going to happen until you get to 0. But you already have an oscillation. All right. So that is something that here, when you get to this point, then you need to change your amortiguators because they are not good anymore. Now, why we don't want this? Now, this is under damping case. Under damping case. This is a warning. We don't want this on mechanical engineering. Why we don't want this kind of behavior? Because we will have oscillations, and oscillations usually break the things. Now, if you, for example, if you happen to have a clip here, alright, so what happens if you do oscillations? Here I'm making oscillations of this. So what will happen is that it's going to break. So we don't want this to happen. We want this to happen. So this is going to go to the rest, to the equilibrium position faster. Here is not going into equilibrium position that fast. And here is going to take longer, and it is going to take longer, and it's going to oscillate. So we don't want this on the parts. So I'm just talking about a car, but it could be a machine. We don't want machines to do this because this is going to degrade or the components of your machine. So we don't want them to oscillate. We want this to happen. All right. So this is the applications. Now on the next video I'm going to cover one problem. No, I'm going to cover amplitude and period and frequency. Some formulas that you will need to solve problems. All right. See you in the next video.